Okay, good morning everybody. Today we are talking about control of salinity. Here you have my email, so any questions that you have after the presentation or whenever you want to discuss anything with me, just email to this address and I'll try to answer to your questions. Let's talk a little bit first about the importance of salinity. This is a map that was produced by the European Union, where you can see with different colors the regions, the areas where there are salinity or salinity problems or problems with sodium. You have different colors for the two different problems, and in many areas both are associated. So you can see the two colors simultaneously. If we focus into Spain, you will see those darker colors in the Ebro Valley and in the lower Guadalquivir Valley. Also, you can see those colors along the coast, and that not only in Spain but also in France and other countries. So this is giving us an idea about the salinity problem in Spain and Europe, but according to FAO, the areas in the world that are affected by salinity are much larger, and they are up to 20% of the areas that are under irrigation. I want to mention a couple of specific or three specific cases. One is when we use groundwater from wells near the coast. When we do that, there is the risk of what we call sea intrusion. If we abstract too much water from the aquifer, there will be a gradient from the sea into the land, and salty water will flow into the aquifers. So that's one of the problems causing damage in the crops, for example, in the area of Almeria. Also, as we will discuss in a few minutes, in greenhouses we have the risk of salinization because we don't have rain. So everything is controlled by ourselves, in this case using irrigation. So let's discuss a little bit more about those points by understanding the salt-water balance of the salt and water balances in the soil. The primary source of salts in the agricultural soils is what we call weathering. The minerals that form the soil can weather, and there will be salt elements that move from the solid phase into the liquid phase. So that would be the primary source, but that is a very slow process. So we will not have a salinization problem caused by weathering, just by weathering in the short term, which means that most of the salts will come from outside. We talk about exogenous sources. So which can be those sources, and that is what we have in the list below. When we irrigate, we use water, but that water is loaded with salts, so that can be a source of salinity problems. We have talked already about sea intrusion, something that happens in the coast, and the problem will come if we use well water for irrigation. We have mentioned before the lower Guadalquivir Valley. There we have natural marshes, areas, wetlands that are affected or are connected to the ocean. So those water tables have usually high content of salts, and they can move into the root zone. We will talk about that later also. And fertilizers. Fertilizers are also salts, or they contain salts. When we apply fertilizers, we apply salts. Okay, so those are the sources of salts, and they come from outside, most of them, as I said. And there are also the ways to remove the salts. How the salts can go out of the system. Well, that happens by what we call leaching. The water that moves through the soil profiles, through the root zone, and it goes away from the system by deep percolation, that water is carrying out salts. So if we look at the diagram, we can see irrigation that, as we said, may come with salts. We have evapotranspiration. The two components, evaporation and transpiration, are water fluxes, meaning that the salts stay behind. When we have, when we observe, when we look at the evapotranspiration process, we should think that most of the flux is basically pure water. The salts stay, as I said, behind. That is what we call evapoconcentration. So if the predominant flux is evapotranspiration, at that point, the salts are going to concentrate. If the predominant flux is infiltration and soil water movement, the salts are going to move away, and at the end, at the lower part of the root zone, they will get away from the system by percolation. Those are the main concepts that we are going to discuss along the presentation, but we will not go far from these concepts. So let's now discuss about the effects of salinity, and we are going to go through three main effects: a specific toxicity, the direct damage, and problems related to soil structure. Okay, let's start with a specific toxicity. We are not going to spend time on this. There are ions that may cause toxicity in the plants or may alter the nutritional processes, and the most common ions causing this toxicity in the plants, ions that are in the salts, are boron, chloride, and sodium. They even at low concentrations in the soil solution may cause problems. There is a specific case when we use sprinkler irrigation. The drops can stay on the leaves, and the chloride and sodium that is in that water concentrate because the drops, the water in the drops evaporate, so they concentrate. They can cause toxicity, but they also can burn the leaves, just because there is a high concentration of salts on the top of the leaf. These effects, these toxicity effects, are more important, more common in tree crops. They are more sensitive. Okay, what we observe, and let's look at the next picture, is along the edges of the leaves, something like burn. Okay, that is the typical symptom of toxicity of sodium. This is a banana leaf. Also, you can see the intervenes that are also damaged. Is also like burn, but you can observe also lighter colors, which means that the symptoms are coming. So those are the typical symptoms of a specific toxicity of sodium and chloride that we see, as we said, mainly in tree crops. Okay, we will not spend more time on that effect, and we will pass directly to what we call the osmotic effect. the salts in the soil solution decrease the soil water potential. Okay, so the plants are going to have more difficulty to absorb the water from the soil solution. That is basically what happens when we have less soil water, less water in the soil. Okay, so at the end, the direct damage of salinity is very similar to the drought damage, to the effect of water deficit in the soil. Okay, so that's the first concept, a main idea that we are going to develop. But before that, we need to understand how to quantify salinity. And we have talked about salts, even I have said concentration of salts. So that's a way to express salinity, grams per liter. We also talk about total dissolved solids, which is concentration, grams per liter. But another very common way of expressing salinity is electrical conductivity. You know that the electrical conductivity of a water solution increases with the concentration of salts. So concentration and electrical conductivity are related, and in fact we have this conversion factor of 0.64. That factor can vary a little bit depending on the ions that we have in the solution, but in general is quite close to this value. So that's the first concept, how to express salinity. The second idea that I want to pass is that when we talk about concentration, we talk about a mass of salts and a volume of water. However, the volume of water can change. The plant absorbs water from through the roots from the soil, so that a volume of water in the soil changes, which means that the concentration is going to change all the time. So we need to standardize electrical conductivity when we talk about the soil. And what we do is to determine what we call saturated paste extract. What we do is to saturate the soil sample with distillated water. Then we extract that paste, that water, and we determine the electrical conductivity in that water. Okay, so we standardize the salinity for a given soil water content, which is saturation. That is our reference. Okay, now, if the value that we find in our laboratory is greater than 4, then we have to start to worry. I want to give this figure as a reference. Okay, greater than 4, we might have problems. Other references for you. The seawater may have electrical conductivity of between 50 and 60. And the units that you read here are decisiemens per meter. Okay, those are the international units for electrical conductivity. In a river, we will have, of course, much lower electrical conductivity. And in wells, of course, it will depend very much on the origin of that water. We may find very low salinity, 0.1 decisiemens meters, or we may find much higher salinity. I have here 5 as a reference, but it could be even higher. Okay, now that we know how to express salinity, let's start discussing a few cases that will help us to understand the salinity problem. In this picture on the left, you see a cotton crop irrigated with drip irrigation. You can see the wetted area, and below that, of course, is the wetted valve, the volume that is receiving or storing the water applied through the emitters. And you may observe also that in the periphery of the wetted area, you appreciate a white color. In this case, that is due to the concentration of salts in that perimeter, in that periphery. What happens here is that we apply the water with the emitter. In that wetted area, there is a flux of water moving the salts away towards the periphery of the wet valve. That is why we observe an accumulation of salts in this white color in the periphery of the wetted area. What you can see on the right is an electrical conductimeter, and the value that you may see there is 14.7, which means high salinity. This cotton crop, that is the salinity of the irrigation water. This cotton crop was suffering, okay, and many crops like this one in the same area were suffering even more that year. And this is another cotton field where you can see that many plants died because of that high salinity. As I said, when you use cyanide water, you cause problems similar to what drought causes. Okay, and in these cases, many plants died, but the other effect is that the growth is reduced, so the size of the plant is smaller than it would be if the water was of good quality. Okay, so we have said already something about the irrigation method. We have talked about drip irrigation, and we have basically said that there is a volume in the soil where there is a flux of water that is free of salts, or it has a low salinity, of course, depending on the salinity of the irrigation water. And at the same time, we have said that there are parts of that soil in the periphery of the wet valve where there is an accumulation of salts. So that is a characteristic of localized irrigation. I have said that the effect is basically the same that drought. So what do you think about applying products like the one that you can see in the picture? I mean, if there is a lack of availability of water because of the low soil water potential, there's nothing we can do by adding anything. So we will have to think about other solutions. I'm showing this because the cotton growers that were suffer the conditions that you have seen in the previous picture, at that time started to buy this type of products, and of course they did not have any effect. But we will come back to these products later on when we talk about sodium problems. Before, we will have to continue with the osmotic effect, and now we want to find or to explain a simple model that relates yield to soil salinity. The model is the equation that you see on the top of the slide, where we have relative yield in percentage. 100% would be the maximum yield, and so the first term on the right side is 100, and then we have the parameter Bs, the electrical conductivity of the saturated paste extract, and what we call the threshold, the salinity threshold. If the electrical conductivity of the saturated paste is below that threshold, we will not have yield losses. Our relative yield will be 100%. Okay, after the electrical conductivity of the saturated paste is greater than the threshold, relative yield will start to decrease, and the decreasing rate with electrical conductivity in the soil is expressed by the BS parameter. That parameter gives us the slope of the, look at the red line, the dashed red line in the figure, okay? That is giving us for a specific crop the relative yield. The slope of that red line is given by BS. The slope of BS is the percentage of relative yield drop per unit of electrical conductivity in the soil. So, depending on where we are in this plan, or where the yield response function for the specific crop is in this diagram, we will say that we have a sensitive crop, a moderately sensitive crop, a moderately tolerant crop, or a tolerant crop. A tolerant crop is in the area where with higher salinity we still have high relative yield. Okay, in the book you have a big table where you can find the parameters of the yield response function for many crops, the ECEU and BS parameters. Here in this picture you see those parameters for 4 crops: wheat, barley, maize, and orange trees. Okay, you see that orange trees are sensitive. So if we draw that the yield function for orange trees in the previous slide, we will find that that curve is in this area, in the sensitive area. Okay, while for maize, we will find that the function is in the area of moderately sensitive crops. Okay, let's do just a very simple example. Let's keep talking about maize on a soil with electrical conductivity in the saturated paste of 3 decisimeters. So if we look at the model of the yield response function, we can enter the electrical conductivity threshold for maize, which is 1.7 decisimeters, and the sensitivity, the slope, BS, which is 12% per each decisimeter. Okay, if we enter that in the function, we will find that relative yield is 84%. We have lost about 16% of the yield due to the salinity of the water, or the salinity of the soil, sorry, which is higher than the threshold for this crop, maize. Okay, but that is a little bit theoretical. It is very useful to compare crops to decide which crop to grow when we have a potential salinity problem. But now we have to deepen a little bit on the response of the crops to salinity. And let's start with this figure, where you can see well, several things. One is the electrical conductivity, but now this is not the electrical conductivity of the saturated paste, but the actual electrical conductivity of the soil solution. As I said before, in the soil we may have a constant mass of salts, but the water content changes as evaporation and evapotranspiration occur. So the concentration of the salts in the soil solution is going to change continuously. And this is important because what the roots are feeling is the actual soil salinity, the actual salinity or salt concentration in the soil solution. So here there are 3 curves, and let's look first on the 2 curves that are below. They represent the soil water tension. You can see that it increases and it decreases, increases and decreases, and so on. And we see that for two depths, 40 centimeters and 60 centimeters. These cycles are telling us that there are irrigation cycles. Every 20-25 days, there is an irrigation event, and so the tension that reaches these peaks goes down because the soil water content increases. So at the same time that the soil water content increases, the electrical conductivity, the concentration of salts in the soil solution decreases. So the problem will be in the peaks of electrical conductivity. That is what is going to damage the crops. Now you can think that low frequency irrigation, which is what we see in this picture, is going to cause more damage than high frequency irrigation that will avoid these peaks of salinity because it will avoid the peaks of soil water tension. Okay, let's look at the next picture where we have basically the same, but in this case comparing low frequency irrigation with high frequency irrigation. In the vertical axis we have the soil water potential. You see that there are ups and downs in the soil water potential due to the irrigation events that are frequent in the black curve, but are less frequent where we have low frequency irrigation, which is represented by the dashed blue line. So in these low soil water potentials, the soil concentration, the concentration of salts in the soil solution will be higher than in the corresponding peaks for low frequency irrigation. So the message here is that when we have high frequency, which is typically localized drip irrigation, we will avoid those peaks of soil water potential and therefore of electrical conductivity, meaning that the crops are going to suffer less if we have high frequency irrigation than if we have low frequency irrigation. So we have mentioned already two features for drip irrigation. One is related to what I just explained about frequency, and the other is that in that wet valve, we have a volume of soil that is with a low concentration of salts, so the roots are going to be happy there, although there is a periphery where the salts concentrate, and so there would be a risk of damage if the plants are planted in that area where salts have concentrated. Okay, just another case, another example that will help us to understand this process of washing salts and concentrating salts. Here we have soil with a water table below, which is at 85 centimeters below the ground level. The salinity in the water table is not too high, but well, it's about 2 decimeters, and what we observe is that the salinity in the soil surface is much higher. It's almost 40 decimeters. What is happening here? Well, the process here is an upward flow from the water table due to capillary rise, and when the water reaches the ground surface, it's going to evaporate. But as I said before, the salts are going to stay behind. They are going to concentrate on the soil surface. So that is the explanation of this high concentration as we approach the soil surface. That's one point. Of course, if there was irrigation or heavy rainfall, the profile will change. Okay, but it will be always affected in this specific case by the water table presence, which limits drainage. So we may have another situations where drainage is not a limitation, and that is what we can analyze in this picture, where we have a salinity profile in the soil before rainfall. That is the dark continuous line. Okay, you can see that salinity in this case increases with depth, simply because there is rainfall that is moving the salts towards the bottom of the root zone. Eventually, a rainfall event, a heavy rainfall event, falls on the soil, and this electrical conductivity profile after rainfall is what we see here. We can see that the profile has moved towards the left, meaning that electrical conductivity has decreased, and that is simply because the excess of water that was applied with that heavy rainfall event drains below the root zone, and it moves away, it washes the salts. That is what we call leaching of salts. Okay, another example, just for you to understand a little bit better this process of leaching and evapoconcentration. We have here the three main irrigation methods. When we use furrow irrigation, we apply the water in the bottom of the furrow. So there is where we have the water flux, there is where we have the infiltration, and where the salts can be transported away from the wetted perimeter. And then if we look at the top of the furrows, is where we see the concentration of salts with that pink color. And that happens there because we don't apply water there, but the water moves towards that top, towards the ridge, and evaporates, leaving the salts behind, and the roots extract water from the ridge, again leaving the salts behind. So with furrow irrigation, we observe that the salts concentrate on the top of the ridge. That is the opposite to what we can observe with drip irrigation when we apply the water on the top of the ridge. There is where the water flux predominates, and in this case, evaporation will predominate in the bottom of the furrow. So it is there where the salts will concentrate. Okay, in this case, the plants will be happier with drip irrigation than with furrow irrigation, because they will have the roots in an environment with less concentration of salts. If we have a sprinkler irrigation, the application of water covers the whole surface, so we will not see differences between the ridge and the bottom of the furrow. It will be a concentration. We will see a concentration of salts which is more or less constant across the field. Okay, so this helps us to understand advantages and disadvantages of different irrigation methods when we have salinity problems, but also I want you to analyze with these examples this balance of water and salts depending on where the water is applied, in which specific area in the field, and where evapoconcentration will occur. There are another two examples here that I invite you to look at carefully. They are simple classical experiments. You will understand just by looking at the two examples carefully, and that will help you to understand a little bit better what I just explained. I leave that there for you because I want to move on to the salts balance. That is what we are going to use to manage salinity in the field. What is the salt balance? Let's think about a system, and our system is the soil solution. Okay, we are going to look at the soil solution where the roots extract water and nutrients. What are the sources of salts for that soil solution? Okay, we have said that the salts may come with irrigation water, and the mass of salts that will come with irrigation water is the result of multiplying the volume of water by the concentration of salts in that water, in that irrigation water. We may have some salts coming with rainfall, although the concentration of salts in the rainfall is very small. Okay, we may have salts coming to the soil solution from the solid phase, ions that are dissolved and move into the soil solution. Okay, we have said before that fertilizers are salts, so if we apply fertilizers, we are applying salts to the soil solution. Okay, so those are the inputs, but at the same time there are outflows. There is a mass of salts that moves away with the drainage water, and that mass is the product of the drainage volume and the concentration of salts in the drainage water. We have talked about salts that can move into the soil solution, but at the same time there are salts that can precipitate. They move from the liquid phase into the solid phase, so they will not be in our system, the soil solution, anymore. And there are some salts that are absorbed by the roots of the plants. Think about nitrates, phosphates. Those are salts that we apply with the fertilizer for the crop to uptake them. So the inputs minus the outputs is the change in the mass of salts in our system that I insist is the soil solution. Okay, let's assume now that there is an equilibrium into the processes of passing from the solid phase into the liquid phase and from the liquid phase into the solid phase. Let's assume also that when we apply fertilizers is for the crop to uptake those fertilizers. So those two sources and outputs, when we add them, are equal. Let's assume that we want to maintain the soil water, the concentration of salts in the soil as it is today. We are happy with that. The crop is not suffering, so we want to maintain that concentration. That means that the increment in S is 0. We will have in what we call a steady state. Then we have the product of the volume of irrigation water by the concentration of salts is equal to the volume of the drainage water multiplied by the concentration of salts in the drainage water. Okay, so that's one thing. The second thing is the concept of leaching fraction. Leaching fraction it's very simple. We have talked about excess of water that has to percolate, that has to drain below the root zone to remove salts. So the leaching fraction is the volume of drainage water divided by the volume of irrigation water. But now, if we use this equation that we have, this simple equation that we have obtained from the salts balance, we see that the leaching fraction is not only the ratio between the drainage and the irrigation water, the volumes of the drainage and irrigation water, but it is also the ratio between the electrical conductivity of the irrigation water and the electrical conductivity of the drainage water. Okay, so the conclusion here is that we can change the salinity or the electrical conductivity through the bottom of the root zone by managing the leaching fraction, by managing the excess of water that we apply. Okay? I leave this example, this exercise for you. We don't have time to do it, but if you have any problem to understand it, just write to me. Okay? I want to show the result of this example, which is the salinity profile, the electrical conductivity profile in the soil for two leaching fractions. For leaching fraction of 2, which is the blue line, and for leaching fraction, well, sorry, not 2, 0.2, and for the leaching fraction of 0.3, which is the red line. You can see that if we increase the leaching fraction, we decrease the concentration of salts in the soil profile. Okay, and we can develop these profiles by using the equation that I just presented, and this is what you can see or what you can do by following the exercise that you have seen in the previous picture, but that we don't have time to do during the class. Okay, so now that we know how to manage the salts in the soil by varying the leaching fraction, we can move to the next concept, which is leaching requirement. Leaching requirement. What is leaching requirement? Well, leaching requirement is just a specific value of the leaching fraction that we have defined before. The leaching fraction that we need to maintain the electrical conductivity in the soil at a given target. That target typically is going to be the threshold of salinity above which the crop is going to suffer. Okay, remember the yield response function. So that's the more common target, but we could assume some yield loss. Okay, and then our target will be a value of the electrical conductivity which is greater than the threshold for that specific crop. But that leaching fraction that gives us the leaching requirement is going to depend not only on the target of electrical conductivity, which depends on the crop, but also on the quality of the water, on the electrical conductivity of the irrigation water. Okay, so once we have the leaching requirement, we can recalculate the water that we have to apply with the irrigation by dividing the requirements, which is in this case the evapotranspiration of the crop, by 1 minus the leaching requirement that we have calculated. How do we calculate the leaching requirements? Okay, there are different ways in the literature to calculate the leaching requirements, but the one that I think is more practical and probably closer to reality is the one that you see on the figure on the right of this slide. Here you have on the vertical axis the leaching requirements, and on the horizontal axis what we call the concentration factor, where we have the two variables that we have mentioned that we have to take into account to calculate the leaching requirements. One is the electrical conductivity of the irrigation water, and the other one is the target electrical conductivity. Okay, so the concentration factor is the ratio between those two electrical conductivities, and we see two curves, one which applies for a conventional irrigation, low frequency irrigation, that is the continuous line, and another line, which is the dashed line, which applies for high frequency irrigation. We need less leaching if we are doing high frequency irrigation, and you should understand that based on what we have explained before. Okay, so you can see here the curves, but also the equations that allow us to calculate analytically the leaching requirements based on the target electrical conductivity and the electrical conductivity of the irrigation water. Okay, that is what you can see in this exercise. It's very simple. It's just the application of those equations for a barley crop that we irrigate with water with electrical conductivity of 5 decimeters. And if we look at the tables that we have presented before, we will find the threshold for salinity damage. And in this specific case, we assume that yield losses may be up to 10% with respect to the potential. So at the end, we find, and I invite you to go through the exercise carefully, we find that the leaching fraction for high frequency irrigation should be 0.02, very low, very low. However, for low frequency irrigation, we might need up to almost 10% of the irrigation water that percolates. Okay, the leaching fraction is 0.095. Okay, so now that we know how to manage irrigation under salinity problems, let's go quickly through the third effect of salinity, which is the problem on the soil structure. What happens? Soil structure can be disturbed, can be altered if we cause dispersion of the aggregates. If we do so, or if that happens, and that may happen due to mechanical reasons, for example, the drops that hit the soil surface, then the aggregates are going to disperse. A crust is going to be formed on the soil surface, and that is going to make more difficult the emergence of seedlings, and it's going to reduce infiltration. All those are problems for the crop, problems for the soil water balance. Okay, that is a problem. Why we talk about that here today? Because sodium causes aggregates to disperse. Okay, so if we have a high concentration of sodium, we are going to have more problems in the soil structure because sodium disperses the aggregates and creates the crust and makes more difficult infiltration. Okay, that's true, but the problem of high concentration of sodium is less problem if we have high concentration of calcium and magnesium, because those two ions have the opposite effect to sodium. So we define what we call the sodium adsorption ratio, which is the ratio between the concentration of sodium and the square root of the average of the concentrations of calcium and magnesium. Okay, so now that we can quantify this problem of sodium, but in relation to the concentration of calcium and magnesium, let's look at this diagram where we can see the sodium adsorption ratio in the topsoil, but also the irrigation water salinity. And why we want to look at both at the same time? Okay, because the presence of other ions in the irrigation water is going to compensate the problem of sodium. So if we have a high sodium absorption ratio with good quality irrigation water, we are going to have problems in the infiltration, and we are going to have problems with crust in the soil surface. Okay. However, if with that same sodium absorption ratio we have high electrical conductivity in the irrigation water, that electrical conductivity is going to compensate the problem of sodium, and we are not going to have problems with the soil structure. Of course, we are going to have problems with salinity, but not problems with soil structure. Okay? I'm going to skip this because it's not so important. And I will end with 2 slides talking about the reclamation of saline and sodic soils. Remember that when we were talking about the salts balance, we said, okay, let's assume a steady state. We are happy with the concentration of salts. We want to maintain that. We are going to manage irrigation to maintain that concentration. But in many cases, that's not the situation. We want to reclaim the soil. So if we have a problem of salinity, I think at this time it's clear for you that the way to reclaim, to recover those soils is applying excess of water. Okay? And we are going to have a lot of drainage, and that drainage water is going to carry away salts. Okay? So here you have an equation that give us an orientation to calculate the amount of water that we have to apply with the irrigation to reduce the electrical conductivity from an initial value to our target final value. Okay, it's a simple equation that of course takes into account the concentration of salts or the electrical conductivity of the irrigation water. So you just look at the equation and you will find how to reclaim a soil based on excess of water. If we have a sodic soil, that is difficult because we have said that if sodium is high, we are going to disperse the aggregates, so infiltration is going to be difficult. So even if we apply a lot of water to leach the sodium, we are going to have problems to infiltrate that water. It's going to be flooded. It's going to stay on the soil surface. So we have to do something. And the most common way to reclaim sodic soils is, yes, to apply excess of water, but after applying gypsum. With gypsum, we are applying calcium, and you remember that calcium and magnesium have the opposite effect of sodium. So that gypsum is going to decrease the sodium absorption rate, is going to alleviate the problem of infiltration due to the problem to the segregation of aggregates, and then it's going to favor to make easier infiltration. Okay, so how much sodium should how much gypsum we should apply to reclaim a sodic soil? That is what you can calculate using the equation that you have in the slide, which is based on the depth of the soil that we want to recover, on the cation exchange capacity of the soil, of course on the initial and final values of the soil sodium absorption rate in this reclamation process, and on the bulk density of the soil. Now I'm showing again the picture that I presented before that applied farmers when they had salinity problems, but in fact what we have here is acid, some kind of acid that will help to alleviate problems related to sodium, problems related to toxicity of sodium, because sodium is replaced by calcium when we add this type of acid to the soil, and then we will alleviate the problem of sodium, but not the problem of salinity. Okay, I stop here because I have used already 55 minutes. Thank you. Any question? Remember, email to my email address. Goodbye.
Thanks, Luciano. Stop recording.